Okay, for part 2 of section 7.3, we're going to look at what we call tabular integration and also solving for the unknown integral. So it's just an extension of what we did last time in terms of anti-differentiation by parts. All right. So if you remember last time we did one where we had the x squared and we wound up having to do it twice. So let's revisit that problem. If we had the x squared again and e to the negative x as our two parts here for our u and our dv, as we call them. What it boils down to is if we do have a special situation like this where we have one of our parts of our integrand that ultimately goes down to 0 in terms of differentiating. If we differentiate that, it goes to 0. And the other part is something that's easy to find an antiderivative for continuously. Then we can use what we call tabular integration. The technique ultimately is this. We're going to write down the actual function. We're going to write down x squared. Then we're going to write it down its derivative, and then finally get down to 0. So we're going to have 4 things in this column, and obviously if the power was bigger, we'd have more than 4. And then on this side, we're going to write down the other part, which is e to the negative x. We're going to write its antiderivative here. We're going to write its antiderivative here, and we're going to write its antiderivative here. All right. So those are my derivatives down this way, my antiderivatives this way. And again, this can be used with any time we have a function that goes down to 0, so namely any polynomial. And then over here, when we have something that's easily antidifferentiable, which ultimately e to the x would be easily to continuously antidifferentiate sine or cosine and so on. And then what we're going to do is we're going to match up these parts. And we match them up as follows. We do the first one times the derivative or antiderivative of the second part. Okay, and we match them up as follows. And we're also going to have what we call changing signs. And so no matter how many we have, we're going to start with a plus here, and then we're going to go minus, plus. And if we had 20 of these, we'd just continue that same pattern. We go plus, minus, and so on. And then we're going to match up these terms. So we're going to have plus as our first term. We're going to have this times this. So we're going to have negative x squared e to the negative x. That's our first term. In this one, we're going to have minus, and the multiplication of these two would be minus 2x e to the negative x. Okay. And then finally, these two, we'd have plus, and then it's going to be negative 2 e to the negative x, and of course we wind that up with saying plus c. Now, if you remember from last time, when we did that by hand, we got exactly that. Okay. We did it by integrating by parts the first time, and then we got another integral that we integrated by parts again, and we wound up with the same thing. Now, however, if you look at the work that I did for this one, much less tedious. Okay? And so if we want to use the solving for the unknown integral, we'll do another one here. We'll do, the tabular integration. We'll do another one here just to practice. We have e to the x cubed cosine 2x dx is our integral this time. So let's try that tabular integration process again. We're going to start out with x cubed, then 3x squared, then 6x, then 6, and then 0. Cosine of 2x, of course, goes here. And then the antiderivative of cosine 2x would be 1/2 sine 2x. The antiderivative of cosine kx is 1/k sine kx. Antiderivative of sine is going to be, of course, negative 1/4 this time cosine 2x. Antiderivative of that is going to be negative 1/8 sine 2x. And the antiderivative of that is going to be positive 1/16 cosine 2x. And just to double check, you can always go backwards and differentiate. If we were to differentiate cosine here, we'd have cosine of 2x, that'd be negative sine 2x times 2. And 2 times 1/16 would get us the 1/8 that we have here. And go all the way back down the line and we make sure we anti-differentiate correctly. Now, when I set up my arrows, again, we're going to start with the top left, going to the second one on the right-hand one. And we're just going to put these together. Remember, we also have this plus, minus issue. And so my final answer here, without having to do all the UDV business, is going to be much simpler to find because I can just take these two and multiply them. I'll get 1/2 x cubed sine 2x. That's my first term. Second term is going to be minus, but we also have a minus, so that's going to be also plus. We have a 3 here and a quarter here, so it would be 3/4 x squared. And then it would be cosine 2x. And then here we have a plus here, but a minus here, so it would be minus 6/8 here. It would be 3/4 again, x sine 2x. And then the last term we have a minus sign, and we have 6/16, that would be 3/8. So we'd have, not a plus sign, but a minus sign, would be minus 3/8 cosine 2x. And of course we ended all with a plus c. So don't have much space here, but ultimately we end up at 5 terms. So this is the first term coming from these two, second term, third term, fourth term, last term of course is plus c. So that's ultimately the gist of the process of what we call tabular integration, which again is a very convenient, more convenient than just the regular anti-differentiation process by parts, because we can get our answer quite a bit quicker. This would take a fair amount of time if we had to anti-differentiate by parts 3 times because of our cubic function here in our first part of our integrand. Okay. Now, there's one other technique that we're going to visit here, and that's what we call solving for the unknown integral. And what it boils down to is if we have one like, let's say, e to the x cosine 2x, so similar to what we had last time, except for this time, the tabular integration is not going to work because ultimately e to the x is never going to differentiate to 0, nor is cosine 2x. Even though these are both easy to differentiate and anti-differentiate, neither one of them goes to 0, so the tabular integration is not going to work. So what it boils down to is that we have two functions like that that are just going to ultimately continue repeating derivatives or anti-derivatives. What we want to do is just set up a normal integration by parts here and have our u be e to the x in this case, and dv be cosine 2x, and it ultimately really doesn't matter which one you let u be u and which one you let dv, as long as you're consistent. So du here would be e to the x dx, v would be 1/2 sine 2x. Excuse me. So if we anti-differentiate, we're going to get that. And then if we do our u v here, we're going to get 1/2 e to the x sine 2x up front. And then our v du here is going to be these two multiplied together, so we're going to get 1/2. We're going to get e to the x sine 2x dx. Right. So right now that is the answer to our integral. It's not okay though because there's still an integral sign in it, so we haven't done anything quite yet. We got part of it out of there, but ultimately we still have almost the same situation we started with here. We have e to the x sine 2x. So if we factor out the 1/2 out of that, then the question is, what do we do with e to the x sine 2x dx? Well, the answer is we do it again. And the good news is that this doing it again business, it's only going to be twice that we have to do this, which, like I said, that's the good news. So we'll let our u be e to the x again. Du is going to be e to the x. Our dv is going to be sine 2x this time. And then our v is going to be the antiderivative of sine here, which would be negative 1/2 cosine 2x. And when we set up our work this time, we're going to wind up with, again, a negative 1/2 out in front here. And our uv, are these two, will be negative 1/2 e to the x cosine 2x. And then our integral of v du here is going to be this times this, so it'll be negative 1/2 e to the x cosine 2x dx. Running out of space a little bit here, but ultimately that's going to be my result when I anti-differentiate this part right here. I'm going to get this. Now, what I'm going to show you right now is that my answer right now reads this. It reads e to the x cosine 2x dx equals this part, which we dealt with already. We already have that out, so we have that part. And then if we simplify this part, we're going to plus 1/4 e to the x cosine 2x. That's going to be negative 1/2 times this part. And then times this part, if we take the negative 1/2 out of there, we're going to have plus 1/2 out here, but this negative 1/2 is going to make it minus again. So we're going to have minus 1/2. Actually, a 1/4, sorry. We got 1/2 times 1/2 because the half's going to come out. And then we have the integral of e to the x cosine 2x dx. Now, here's where we have to be a little bit creative here. Ultimately, in our sentence here, we have this, and we have equaling this minus this. Well, what do we notice about this right here? Okay, this is ultimately the same integral as what we have over here. So if we took this quantity right here, which ultimately is minus 1/4, and we add it to the other side, if we take this whole quantity right here and we add this to both sides of the equation, it'll be gone over here. And over here we have one of these plus 1/4 of these, so ultimately we'd have 5/4 of e to the x cosine 2x dx, because they're like terms. Notice they're the exact same integral. So if they're the exact same integral, then they are like terms. If we have one of them over here and we have 1/4 that we're going to add, we're going to have 5/4 times that equals 1/2 e to the x sine 2x plus 1/4 e to the x cosine 2x. Now, we might say, well, how does that do us any good? Well, remember what we were setting out to find is the answer to this. Okay? Well, isn't that right here? Okay. Certainly. So what are we going to do to get that alone? We're going to get rid of the 5/4 out in front by dividing by 5/4 or multiplying by 4/5. And ultimately, if we do that, 4/5 times 1/2 is going to be 4/10 or 2/5 e to the x, sine 2x that is. And then if we do the same thing here, if we multiply this by 4/5, we're going to end up with 1/5 e to the x cosine 2x. And of course we have to add c to the end of it, and we're done. So that process is what we call solving for the unknown integral, and ultimately it's going to be used when we have two different parts here where they're not going to differentiate down to 0, so the tabular integration is not going to work, and no matter how many times we did anti-differentiation by parts, we would never be able to come up with a final answer to that. But when we solve for the unknown integral, all we have to do is do it twice, because when we wind up with this situation and we have this and this being like terms, we can put those together. And if we put those together, then it's a matter of just dividing to get that part alone. And then the integral, what we set out to find, is going to be equal to this, and we're good to go. Okay. So that's the gist of anti-differentiation by parts. It takes some practice, just like substitution and the other techniques that we've learned for anti-differentiation. It takes a little bit of practice to make sure that we can get this right each time. So that's why we're going to do our homework problems now to practice this technique, and we'll ask questions later. So good luck.